Today we're going to look at an open-ended investigation called ever-increasing rectangles. So we start out with a rectangle, and then the process is to surround it with other squares. So we've got the top, the bottom, the right and the left. And I know we no longer have a rectangle, but we started out with a rectangle and then it's kind of increasing in size. What we then do after that is do the same again. So we'll add this sort of blue coloured square to on top, and then some around here, and then we just sort of keep going. We keep surrounding the shape. So the fourth one, we'll just be adding one to around like this. So what I'd like to do is pause the video and think, what mathematical questions could we ask about this? All right, here's a couple. How many squares are how many squares are in the fourth pattern? I mean, how many squares are in the first, second, third pattern, for example? Fourth pattern. But even better, can we work out the number of squares in any of the patterns? The 100th pattern, for example. Or how about this one? What if we start with a different configuration? I've just chosen 3 by 1, but we could go with maybe 2 by 1, or maybe 2 by 2. We could start with a square, or 4 by 3, for example. Is 4 by 3 going to be the same as 3 by 4? That's another question. So what I want you to do is pause the video, investigate, and generalize. Now, if you're not sure what to do, I'm going to go through one as an example. I'm going to go through this one that we have here. So I've got 3 squares in the first pattern, and then you can see that I'm adding 6, 7, 8. I'm adding 8, so it's going to be 3 plus 8, which is 11. And on this next one, I've got my 11, and then how many am I adding? If I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's 3 plus 8 plus 12, which is going to be 23. And I've formed a sequence. We might want to think about how many would we add next. Well, I can, actually, I think it's worth doing just to get a feel for it. So I'm going to add 1, 2, 3, and then there's going to be 1 here, 4, 5, 6, 7, 8, and then 1 at the bottom, 9, 10, 11, 12, 13, 14, 15, 16. So the fourth one is going to be 3 plus 8 plus 12 plus 16. And you can see the changing difference. On this one I added 8, on this one I added 12, and now I'm going to be adding 16. So you can sort of see that basically the difference is going up every time, but it's going up by a constant amount, by 4. And actually this is going to be a quadratic sequence, and that is essentially what we're investigating here. So let's go with the pattern. We've got 3, 11, 23. And I'm just going to remind you of the process for finding the nth term. If we find the first difference, we've got 8. Let's do this in a different color, sorry, just to make it clear. 8 and 12. And then the second difference is 4. And if you wanted to check, you can see the next one it was 16. Yes, it's definitely 4. Now let's write down our nth term for a quadratic sequence. an squared plus bn plus c. And I'm going to write down those terms. So the first term is going to be a plus b plus c. The second term is going to be 4a plus 2b plus c. And the third term is going to be 9a plus 3b plus c. This is what I want you to be practicing today, this skill. I'm assuming that you've done this lesson already on nth term of quadratic sequences. So the first difference is 3a plus b, like this is a recap I'm doing here, and 5a plus b, and then the second difference is 2a. So it must be that 2a is equal to 4. So a is equal to 2. it must then be that 3a plus b equals 8. Well, a is 2, so it's going to be 6 plus b equals 8, and b is 2. And then a plus b plus c must equal 3. So 2 plus 2 plus c equals 3. C is going to equal minus 1. And we've worked out the nth term. It's going to be 2n squared plus 2n minus 1. We can check that for maybe the fourth pattern to see if it works. So when n is 4, we're going to get 4 squared, 16, times it by 2, 32, plus 8, 40, minus 1, 39. And if I was to add 16 on to 23, I would indeed get 39. So I can be pretty sure, like, I haven't proven for sure that it's a quadratic sequence. That's got to be said. Sometimes things look like they're quadratic sequence, and actually they might even look like the quadratic sequence for, say, 10 terms, but then fail. But here, I'm not going to go into proving that it's a quadratic sequence, like, for sure. Here, we're just gonna ignore that aspect, but it will be, okay? So we've done it for this one. We've found the nth term, but that is for 3 by 1. So I should just make a note of that. And I'm going to call it the width is x. X is equal to 3. And then the height is 1. So we've done that. But what about now if we start with a different configuration? This is where I want you to really run with it. Go for it. See what you find out. See if you can investigate and generalize. That is the main purpose of this lesson now. Good luck. Here are some that I did earlier. So I've got different widths and I've got different heights. Notice I do a 3 by 2. I don't worry about a 2 by 3, for example, and that's because if you swap the x and the y around, you'll get the same nth term. It doesn't matter if you turn this round to make it a 1 by 3. You'll get the same pattern coming out. So I've just made sure I've not double counted, and maybe you did. Maybe you realized that you got the same during it. I'm not sure. I've written down the first 5 terms for each one. And then I've written down the nth term, so you can check if you were correct. And by the way, this n with a little triangle 2 means n squared. I've used sort of a kind of computational notation for that. You might want to think about what patterns you see. And I see that if I keep y fixed, well, actually, the first thing is that we always get 2n squared. Because we're always going up by 4 actually each time, with the second difference, that is. But then we get some interesting things going on with this n term. The n term is going up by 2n each time for this, and actually it happens to be the same if you fix the height and increase x, or vice versa. That is, actually you go up by 2n. The constant is a little bit trickier, but I think generally if we're keeping if we're keeping y fixed and increasing x by 1, then actually the constant term goes down by 1, I should say. Does that happen? Actually, no, that doesn't happen here. So that's a more complicated situation. Here goes then. How could you, like, if you've done that, if you found some results a bit like that and just looked at the patterns and tried to figure out what might be going on, then here's a smiley face. Okay, you've done well. Good job. I'm going to show you now how we can generalize even further. It's going to get a bit complicated now, but let's go for it. How can we deal with it? And by the way, if you want to, if you think, I'm kind of understanding what's going on, I'm going to try and finish this myself, then pause the video, give it a go. I'm going to explain how we can get the nth term for an x by y rectangle. And the answer is going to be in terms of x and y. Here goes. So, First of all, I'm going to draw a starting rectangle. Now, I'm going to actually draw some squares in, but I don't mean it to be a 5 by 3. I just kind of have it just to give a bit of a feel for what's going on. In fact, it's going to be x along, like the process will be the same, and y in height. Now, if it was 5 by 3, I'd have 3 lots of 5. I'd just multiply them together. The same is going to apply here. My first term, the number of squares, is just going to be xy. Now, what happens if we if we go through one application of adding extra squares? Well, this is going to happen. I'm going to add on some squares along here, and there's going to be x lots of them. I'm going to do the same at the bottom, and there's going to be another x lot of them. So my second term is going to be xy, what I had at the start, plus 2x. But I'm not done, because I can do exactly the same for y. I'm going to add on y lots here and y lots here. So that is going to be my general second term. You can see it happening here. So I just added, I started with 3 by 1, I added 3, I added another 3, I added 1, and I added another 1. That's me adding 2x plus 2y. Right, third term, this is going to be the trickiest one. So we're going to start out, let's write the full thing out. It's going to be xy plus 2x plus 2y is my starting amount. And then I'm going to again add on x here and x here. So I'm going to add on another 2x essentially. And then I'm going to do the same for y. I'm going to add on y amount of squares and another y amount of squares. So another 2y. And just to finish, I've got these ones in the corner. So 1 here, 1 here, 1 here, and 1 here. I'm actually going to be adding 4 on. And you can see that happening for the first pattern. These ones in red. So I'm adding on another lot of x, another lot of x, another lot of y, another lot of y, and I've got these 4 here that I'm circling. This extra one. Okay, I'm not going to worry about the fourth term. I've got enough. I know it's a quadratic sequence. I've got my first 3 terms, albeit in terms of x and y. Just need to tidy this up. So the third term is actually going to simplify to xy plus 4x plus 4y plus 4. Okay, I'm going to actually cross that out. All right. We're getting there. So the first difference is going to be 2x plus 2y. And here it's going to be 2x plus 2y plus 4. I'm just finding, I can see that I'm just subtracting them in my head. I'm doing xy minus xy, that's nothing. 4x minus 2x is 2x. 4y minus 2y is 2y, and I've got this extra 4. So that's where that came from. These are my first differences. And then the second difference is just going to be 4. And we're nearly actually there, okay? So we know that is, I'm not going to go through all the steps here, but I know that 2a is equal to 4. Remember, I've got my general quadratic sequence here. In fact, let me bring it down. Okay, so in theory, you derive this from scratch, but by this point, we've done it a lot of times. I'm not gonna do it. There we go. So I'm comparing 2a with 4. Let me circle it, and I'm going to get that a is equal to 2, which is what we find throughout. It always is 2n squared. Next bit, we've got that 3a plus b is equal to 2x plus 2y. 3a plus b. So we know that a is 2, so b is going to be 2x plus 2y minus 6. That's going to be the answer. I've just substituted in 2, done 3 times 2, and I've subtracted that from both sides to give me b. And finally, I know that a plus b plus c is going to equal x, y, because that is my first term. I'm just comparing this with this. So a is 2, b is 2x plus 2y minus 6. And I've still got my plus c, and that is equal to xy. So where does that leave us? That leaves us that c is going to equal xy minus 2x minus 2y. 2 minus 6 is minus 4, so I'm then going to add 4. And I'm done. Okay, I can write down that my nth term is 2, remember it's here, oh, I haven't written it down, but it's an squared plus bn plus c. So it's going to be 2n squared plus 2x plus 2y minus 6n plus xy minus 2x minus 2y plus 4. You can leave it like that, and you know, that will always work from now on then. So, you know, this is where actually I got this table from. You can just substitute in your values for x and y, and it will all fall out, all of these nth terms, so you can check them. This is, you know, I quite like the way it's written, because you've got your n squared term, you've got your n term, and you've got your constant term. You could play around with it and maybe simplify it slightly. Let me show you how. So we could leave it like that. Here you can actually factorize out 2. So it's going to be x plus y minus 3. And I don't know, might just be slightly nicer. Here, it's not loads you can do, but you could factorize out 2 with the x and the y and write x plus y. Okay, but I probably would say, like in my answer here, actually I kind of brought it, I wrote all the terms out that didn't involve x and y, the first 3 terms, and then I wrote the other ones like this. So that's another way of writing it, but probably this is, you know, this is as good a way as any of writing it. So if you manage to get to that, that's brilliant. If you manage to understand it, that's brilliant as well. If you've had a good go at this investigation, then well done. You know, it's practicing, finding the nth term of quadratic sequences. The aim was also to show that, you know, you can, like maths, you can take it quite far. You can generalize it and actually write down a general formula, which admittedly is, you know, it doesn't look that simple, but in fact, it's, you know, any starting rectangle now, we can work out any number of squares for any number term. So that is pretty impressive, I think. Well done.